All right, let's talk about something that's absolutely critical in industrial cybersecurity. How do you take a massive, sprawling, and frankly complicated operational network and break it down into pieces you can actually manage and defend? That's right, we're diving deep into segmentation and zoning. So here's our game plan for today. First, we're going to make the case for why you even need to divide your network in the first place. Then we'll pop the hood and look at the toolkit for actually doing it. After that, we'll see how we go from just dividing things to really controlling them, how to keep data safe when it's moving, and finally, we'll tackle the next big thing, the industrial wireless challenge.
So let's start at the very beginning. You might be wondering, why can't we just have one big, flat network where everything can talk to everything else? I mean, it sounds way simpler, right? Well, in an industrial world where the stakes are so high, that kind of simplicity is actually a huge, gaping security risk. Let's dig into why that is.
The whole idea boils down to this: network segmentation. And we're not just taking a butcher's knife to the network here. This is a really precise technique. It uses something called subnetting to create these smaller, self-contained networks that actually mirror the way your organization is structured. Think of it like building digital walls between different departments or functions.
And here's what that actually looks like. You can see the central router there acting like a traffic cop, making sure data only goes where it's supposed to. Finance has its own little neighborhood, production has its own, and so on. This setup enforces a really simple but powerful security idea. A computer in R&D has absolutely no reason to be talking to a machine on the factory floor. And with segmentation, that's just not allowed to happen.
And you know, the cool thing is, this isn't just about security. For one, you get a massive security boost, because if an attacker gets into one segment, they're trapped. They can't see or move to the others. But you also get a big performance jump, because you're not drowning the whole network in traffic that's only meant for one little corner. And finally, when something inevitably breaks, it's contained. A problem in one segment stays in that segment, which makes finding and fixing it so much faster.
Okay, so we get why we need to do this. Now for the fun part. How do we actually do it? What are the tools we use to build these digital walls and create our secure little network neighborhoods?
First up, we've got a tool that most of us are using every single day without even realizing it: Network Address Translation, or NAT. The main job of NAT is pretty simple. It hides the real IP addresses of all your internal devices from the big, scary internet. It's kind of like giving your entire network a single public mask to wear.
And here's a peek at how that works. See, to the outside world, there's just one public IP address. But behind that NAT router, you've got a whole bunch of devices, each with its own private address. That router is working overtime, constantly translating between that one public address and all the private ones, basically acting as a gatekeeper that cloaks your internal setup from anyone snooping around.
But, and this is a big but, NAT isn't the magic security bullet you might think it is. In fact, it actually gets in the way of some of our best security tools. Because its whole job is to rewrite the source IP address on a packet, it completely breaks any protocol that relies on that address for authentication. Something like IPsec sees that the address has been tampered with and immediately shuts the connection down. It just doesn't work.
So what's a better way? Well, let's talk about something way more powerful and flexible: the virtual LAN, or VLAN. This is where things get really smart. A VLAN lets you create totally separate, logical networks that all run on the exact same physical hardware. This is a total game changer, because you can redesign your entire security architecture without having to unplug or move a single cable. Just take a look at this. We have one physical switch, but we've told it, hey, ports 1 and 2 belong to the executive VLAN. Ports 3 to 5 are for finance. So even though they're all plugged into the same box, if a computer from sales tries to talk to one in finance, the switch just says nope and drops the connection. To the computers themselves, they might as well be in different buildings.
And this is where it gets really powerful. We can start stacking these VLANs to build a serious, multi-layered defense. In this model, the firewall is protecting the crown jewels, the OT tier, the network that's actually controlling the physical machinery. To get there, you have to pass through a database tier, an application tier, and a web tier. Each one is its own island, which means an attacker can't just hop from your website straight to the factory floor.
Okay, so building the walls is step one, right? But walls are pretty useless without guards at the gates. Now we have to define and enforce strict rules about what's allowed to move between these zones we've created. This is where we go from just dividing the network to truly controlling it.
Exactly. If segmentation is drawing the map of our city and building the walls, segregation is writing the laws and posting the guards. We're now creating and enforcing a rule book that says exactly what data can go where, who can send it, and what it's allowed to do. It's all about active control. And this brings us to a really fundamental choice in security: blacklisting versus whitelisting. Blacklisting says, allow everything unless it's on my list of bad stuff. Whitelisting flips that completely. It says, deny absolutely everything by default and only allow this very specific, pre-approved list of traffic. And let me be clear, for any serious industrial security, whitelisting is the only way to go. It's not even a debate.
And when you use that tiered model we just saw, making these rules become super clear. Data can only move between zones that are right next to each other. So the web tier can talk to the application tier, sure. But any traffic trying to leapfrog a layer, like something from the web trying to talk directly to the database, is immediately flagged as illegal and gets blocked. No exceptions.
Okay, so our zones are set up. Our rules are in place. Awesome. But what happens when we actually need to send sensitive data from one zone to another, or even worse, across the public internet? How do we keep that data safe while it's in transit?
Well, the answer is a really cool technique called tunneling. The idea is brilliant in its simplicity. We create a secure, private, encrypted tunnel for our data to travel through a network we don't trust. And we do that by taking our original data packet and wrapping it up inside another public-facing packet.
And this diagram really breaks down how it works. You can see the original data packet at the top. First, it gets encrypted, so it's just scrambled nonsense. Then, that entire encrypted packet gets stuffed inside a brand new packet that has a new destination header. So if someone is snooping on the network, all they see is that boring outer packet. The real data, the important stuff, it's tucked away inside, completely hidden from view.
All right, for our final piece, let's talk about the next big challenge: wireless. Up to now, everything has been about securing physical cables. But more and more, industrial sites are cutting the cord. And believe me, that changes the game completely.
So this is the dream, right? Getting rid of all those long, expensive, and frankly annoying cable runs. The idea is to have these networks of wireless sensors all over the facility, feeding data to local gateways, which then send it all back to the main control center. It's flexible, it's scalable, and it looks great on paper.
But wireless isn't just one thing. It's a whole family of different technologies, each built for a specific job. You've got your standard Wi-Fi, of course, and Bluetooth for close-range stuff. But in the industrial world, you see more specialized things like Zigbee, which is great for low-power sensors, and even wide-area tech like WiMAX.
Yeah, but here's where that dream bumps up against reality. Industrial sites are electrically noisy places. You've got huge motors, high-voltage switches. All that stuff is basically screaming electromagnetic noise, and that noise can just wreck your wireless signals. A delayed or garbled packet is a disaster for a control system that needs data right now. Oh, and every one of those wireless sensors? It needs power, which means either running more wires or dealing with the nightmare of changing thousands of batteries. So this all leaves us with a huge question to think about. We've spent all this time learning how to build digital walls and control the flow of data through physical wires. But what do we do when the network itself is invisible? How do we adapt all these core security ideas to protect our most critical physical systems from threats that are literally just floating through the air?